All right, so we just finished up kind of talking about forces on an object on a slope. Even when we're pushing horizontally against the object, we learned that essentially we're looking at three different triangles. Today we're going to take a step back and we're going to look at something quite a bit easier. Um, we're going to look at spring constants, or the forces provided by springs. Springs are a very simple tool. Really what they do, to make it, you just kind of coil some wire around. It's more complicated than that. But really what we're finding is with springs is when we compress a spring, it's exerting a force to try to get back to kind of however long it was before we compressed it. And the same is true for stretching it. If I stretch a spring, it's wanting to pull in to get back to that length it started at. So we know that there's a force provided by springs. And people smarter than I have figured out how to actually calculate how much force that is. So what they do, and let's even just call this force spring. To figure out the force of the spring, what they've done, they've experimentally shown, and we might, thank you, um, go through and actually figure this out for ourselves. We have some scales, some springs we can use to actually solve this. Really what they find is that the force of a spring, whether it's compressing or from being compressed or being, stretched out, is equal to a constant called the spring constant times, you're going to see this a couple ways. Really, this is still kind of distance, but in this case, it's the distance the spring is stretched. All right, so really what we're looking at, and granted, like if you go online to check this out, you can find this a bunch of different ways. Like a lot of places are going to make your K negative just because they say like it's always in the opposite direction of whatever force is being applied to it. Sometimes instead of D, you'll see like delta X because really it's a change in position. Really, the distance the string is being stretched, we're going to go through it here in a second. All right, so this is our main equation we're using. So let's say that I have a spring. It's suspended from a ceiling, a desk, doesn't really matter. And starting off, my spring has a length of 22 centimeters. I then place a 2 kilogram mass on that chain. So I know like intuitively, if we put a mass on my spring, gravity's gonna pull it down. I have F of G pulling it down. But really that doesn't happen until we've stretched our spring out, okay? And then we have the force of the spring kind of pulling back up. So we're gonna calculate that. This isn't going to be very complicated at all. What I need is I need a spring constant. And we're gonna say when I opened up my box here for my spring, first thing I need to do is I need to figure out what's the force of gravity on this guy. All right, so the force of gravity, because at this point, at this length, the force of gravity is equaled out by the spring's force, right? Like once it's stretched, like it's still pulling up, but gravity's no longer, moving it downward. It's still pulling it downward, but there's no acceleration downward. So first thing I would suggest doing is let's find f of g is equal to 2 times negative 9.81 meters per second squared. We should have kilograms there. And I'm going to guess that we end up with negative 19.62 newtons, I think, is what we're going to get there. I have a calculator. We can do that quick. 2 times 9.81, 19.62. Good. All right, move that off to the side. So that's how much, thank you. So that's how much we're pulling down on this, that mass is pulling down on that spring. I don't know the force that the spring is exerting upwards as well. because f of s is equal to that, just, minus, reverse the sign. I mean, these two things are opposing forces. At this point, it stopped moving. All right, so now I can calculate out what my spring constant is. I know my force of the spring is 19.62 newtons, and that's equal to spring constant's what I'm looking for. D. All right, so now for D, what I'm going to do to figure that out is essentially I'm going to take its final length, so 38, minus its initial length, so 22, and I should get 16. All right, so now I just need to get K by itself. There's a point there. All right, so I just got to take 19.62 divided by 16, and I get a spring constant, if I had remembered to move that off to the side, of I'd call that 1.23. All right, this thing will probably have some units on it. All right, so let's actually figure that out too. So let's see, centimeters canceled out. We could call this, if I remember to put newtons here, I had newtons per centimeter. And that's a perfectly acceptable unit here. This tells me just how much force is exerted per centimeter of stretching of the spring, and that kind of makes sense. The less I stretch it, the less force that spring is pulling to kind of come back in, if you will. Whereas the more I stretch it, the more that spring's trying to pull back into its original shape. All right, so let's kind of look at that one more time. So in this case, I tell you the downward force on the object, it's 100 newtons. We could even say that that's negative 100 newtons downward. That means there's positive 100 newtons kind of pulling back up on it. That'd be my F of S. And this time my spring just stretches 2 meters, go from 1 centimeter to 3. So we're still using F is equal to KD. All right. We know that force is 100 newtons. K is what we're looking for. Change of distance though, 2 meters. So this is a sizable spring. This would be something we would see in an industrial setting. Maybe research looking at this type of thing would be kind of how they would get masses of very, very large objects as well. So 2 meters is kind of my distance, 3 minus 1. 3 minus 1 is 2. So now find K, just divide both sides by 2 meters. I'm not even going to get out the calculator for this one. K is equal to 50 newtons per meter. Pretty basic, right? Springs will get interesting once we start having them go sideways, having them start like pushing things, start looking at things like pinball machines, stuff like that. But I think that's a pretty good introduction to springs and force. Other than that, good luck with the practice problems and ask me questions if you need.